Okay, so let me begin by recalling a few things we have done. So I think we considered the simplest case. In some sense it is simple, but it's as general as it can be. We talked about a electromagnetic plane wave oscillating in the XY direction and propagating in the Z direction. What do I mean by that? So you would have so this would be, when I draw this, it means at this point, that's the electric field. That's what I mean. At this point, that's the electric field. Okay? And so this is the magnetic field, and the whole wave propagates in the Z direction. The wave itself propagates in the Z direction. So I'll put V, but V equals C in vacuum. So let me write this. So this is again written as a complex electric field. And the only thing that makes it complex is this initial thing, so that we don't have a phase appearing in the exponential. And this is in the x hat direction. And e to the I, it's moving in the moving in the z direction. So z minus omega t. And b is equal to, same thing, b0. But we had an expression for b0. We'll get to that as well. I kz minus omega t. We can easily get an expression for, in this case, the propagation velocity. So you set kz minus omega t equals 0. That's sort of the peak of the wave, if you will. And then you get that z over t, distance traveled per unit time, is omega over k. And omega, as you know, is 2 pi times frequency, and k is 2 pi over wavelength. So you get f lambda, and that is indeed the speed of the wave. Okay? But we had few more facts. One is the fact that E or EZ equals 0 equals BZ. In this context, since the wave is propagating in the Z direction, we would say that it is a transverse wave. And we also had an expression. This is complex. K over omega. This is Z hat cross E0. And if you want, using this expression for omega over k, or k over omega, this can be written as, 1 over c z hat cross. Now, if you look at this and this, these guys are real. So whatever is the complex part of B is the complex part of E. So from here, we actually conclude that E and B are in phase. I think this is sort of where we were. If we didn't write it using this complex notation, after all, the physical field is real, I would write this as E z t equals, look at this, I'm trying to get rid of this tilde. So again, I won't make much of a change. I would write it as E0, and I'm taking the real part, so I get cosine kz minus omega t plus delta. So the price of going from complex to real is two things. First of all, I have replaced e to the I with cosine, and the complex part of it creates a phase shift. And and this is the real part, and this is what we care about. This is also presumably what we're graphing. And so look at this. All I have to do is worry about the direction. The magnitude of this is, the magnitude of B is the magnitude of E over C, because these are a unit and they're perpendicular to each other. So it just becomes E0 over C, no choice. They're in phase. And indeed, Z cross X is Y. This is, sort of the prototype for a plane wave. Yeah? So one thing we want to do, not that we'll do much with this can easily be generalized to a direction n hat. So this, I would want to call this the propagation direction. No. That is not propagation direction. There are names for these guys, so I should be careful. It is the direction of k. That is the propagation direction. So propagation vector is k. So I'm going to define and n is perhaps the polarization direction. Direction of E. Let me put it this way. So what do I mean by that? I'm going to take this expression and write it for not just this case, but the arbitrary case. It's so easy to generalize. And here it is, E vector, let's make it complicated. See, here we had Z and T. I'm going to make it R, any direction that we want. And then, of course, I get my complex amplitude. And we know that by the definition of notation, n is the direction of E. So I put n hat e to the I minus omega t instead of z, kz. I'm going to now have k dot r. In this wave, it was moving in the z direction, so I just put it as kz. Here it is moving in the direction of k. So kx times x, ky times y, kz. Okay, and so similarly, I would want an expression for b, and b would be equal to b0 e to the I k dot r minus omega t. But let me hang on to this expression. So I'm going to continue here because I want to do this.
Okay.
Yeah.
What is the kind of difference between R, like the directions between R that's dependent on the K propagation vector?
So,
In the previous example, they're both Z's.
correct, because the strength of the electric field in the plane wave depends only on the z coordinate
Yeah.
at any given time.
Yeah.
Here, it depends on the x, y, and z coordinate, because the plane wave could be moving in this direction.
Yeah.
Yeah, it is not aligned with the axis.
Okay.
So the direction of propagation is k.
Yeah.
Yeah? So, see, k times z can be, this is sort of a scalar version, can be thought of as kx times x plus, or can be thought of as k dot z hat, right? Because it has only one component. So what we want to do is, in general, we want to get this to go to k dot r, so that it can go in any direction. Which direction would it go? Well, ultimately the direction of k. Yeah? Yeah. So in this case, B0, we have a nice expression for B0. So over here, I have B. See, this vector B0 is related to E in this form. So now I can write it as either K over omega or C. Now tell me, what is Z? That's the direction of propagation. So what do you think it's going to be over there? K hat. Good. Cross, this doesn't change, right? E to the I, K dot R minus omega T. I can simplify so many things. I can write, well, and I think I'm going to choose the version that the book prefers, which is, again, 1 over C, K hat, cross. I can take these two in and write it as yeah? So I know I have written this in a sort of a scattered way, so let me, at least for your notes, bring attention to the final form. If it's propagating like so, that electric field is given by this, that's the final form. And magnetic field is easy to remember. Don't worry about details, there's always that. And this, when you apply it to the previous case, will just work out. Yeah? There's one caveat in here, it's a transverse wave. We haven't specified that so far. So there's a condition here. The propagation, the electric field is perpendicular to the propagation direction. So this is also B and B to B. Let's pause for a second. Let me take any questions that you might have.
When we circled our B in the blue, is that the complex form of B?
It is the complex form of all of B, yeah, correct. So because what I did was I took this and subsumed it into the actual vector. And K over omega is 1 over C. So these are the facts to remember. Have this picture in mind, and we'll do most of the things using this picture, because who's going to think of a wave going southwest at 37 degrees. It's easy to just align the axis, right? Okay. Now what I want to do is talk about the energy density of a plane wave. If you recall, this was the case, correct? Density. Yeah, not total, not, yeah. See, but I look over here, and then I look at this guy. This is 1 over c squared. And the magnitude of this is still E, because K is perpendicular to E. How do you know K is perpendicular to E? Because of this condition. So this is just E squared. So U takes on a simpler form. Let me do it this way. Epsilon naught E squared plus 1 over mu naught C squared E squared epsilon naught plus epsilon naught mu naught over mu naught, that factor, E squared. What did I do here? I replaced C squared with 1 over epsilon naught mu naught, because C is square root of 1 over epsilon naught mu naught. And this is sort of gracious enough to cancel. And you get that for a plane wave, that is a simple expression for the energy density. And we'll compute all of this for a plane wave. In fact, we'll compute it for this. And then you can see we can just write the general direction very easily. Now the pointing vector. What is a pointing vector? It's the energy crossing per unit area per unit time, right? So if you look at any patch, yeah, this is S. Oh, it doesn't have to be. It looks like it's perpendicular. It doesn't have to be perpendicular. So it's the energy crossing the surface per unit area per unit time. That is what it is. And this is 1 over mu naught E cross B. Again, E and B is perpendicular. E cross B is in the, so let's compute this for a plane wave of this type. Yeah? So what is the direction of E cross B? Z, because X cross Y is Z. So I'm going to apply it to this particular case, and let's see the expression we get. This is equal to propagating in the Z direction, S hat 1 over mu naught. E is perpendicular to B, The strength of E is E. The strength of B is B, which is E over C, correct? So it becomes E over C Z hat. So I can write this as epsilon naught E squared C hat. Correct? And then momentum density. What is the momentum density? Sorry? Yeah, could you check epsilon naught? It sounds about right. So that is going to be epsilon naught over C E squared C hat, because B is nothing but E over C. Yeah? Let's see if I've picked a different version. Nope, that is it. Now, consider light. Consider light. It oscillates pretty rapidly. I think Griffiths even gives an example. The period is 10 to the minus 15 seconds. When you say visible light, somewhere in the middle, right? I mean, there's a spectrum. Visible light, and this is why he says approximately 10 to the, make sure I'm accurate, minus 15 seconds. This is rapidly oscillating. It is going through 0 to 1 to minus 1 to 0 in 10 to the minus 15 seconds. So if we measure any Poynting flux, any quantity, will we get a meaningful number? And what uses it to get the value of the electric field at an instant in time? So for everything, the waves are oscillating so fast that you at least want the average of it, some sort of a period, okay? So remember, just in magnitude, E is E0. Let me put it this way: cosine kz minus omega t plus delta. Yeah? And of course, we want all of these expressions have E squared in it. So I have yeah? So how do I get the average of this? So what do I want to do? I want to do cosine squared kz minus omega t plus delta. Then I want to integrate over t through one period. What is the period? 2 pi over omega. Omega is 2 pi over t, correct? So this is what we need. You can easily do this integral. this is not very difficult to do. You can see this kz and delta does not matter. But Griffiths has a neat way of doing this. It's 1/2. We'll see why. Listen, the details are not important. Cosine squared theta plus sine squared theta equals 1. What does cosine look like? Cosine squared look like over one period? It's going to look like, yeah? This is cosine squared theta. What is sine going to look like? Do you expect the average of cosine and average of sine to be different? They're just moved around slightly. Over an entire period, it's going to be the same. So the contribution to this and contribution to this should give you 1. But these two guys are the same. So if you don't believe it, knock yourself out is what Griffiths is saying. Why stress over it? I mean, the area under this, you see, this area versus this area, and this portion, you can see goes into that. You see, these two parts go in here. They add up to be 1. So it's just 1/2. I think it's a footnote there. Oh, I have to be careful. That's not true. It would add up to be the period. So you have to. This is just 2 pi over omega. Right? So it's not 1/2, so I have to divide by 2 pi over omega. That'll give you 1/2. You see what I've done here? Look. So this is the true average, right? You integrate it and divide by this length. Yeah? So that means the average value, the expectation value, this is the average over one period. This notation is look at this, and I go, well, epsilon naught, I have a E0 squared, and then the average, which means you integrate it over a period and divide by the length of the period, divide by the period, so I simply get. Yeah? What about the average of S? Well, that's easy. I put 1/2. Oh, E0 squared. And put the momentum squared. Average momentum density is 1 over 1/2 epsilon naught E squared over C Z hat, and isn't that just U over C? correct? A little bit of terminology. It's in the book. You just hang on to it. I don't recommend you, unless you're working with constantly, you won't remember these definitions. Just look at this. The average of the Poynting flux, that's the average power per unit time. That is nothing more than intensity. Intensity, intensity. Look, it's not the vector, huh? Intensity is just the magnitude. So that is the energy crossing a surface per unit area per unit time. Yeah? Again, I wouldn't memorize all of this at all. I just know where they come from and go to the textbook as needed. It is really applying the expressions we had previously. So when radiation shines on a surface, let's look at this. For a perfect absorber. And let's, for the simplest case, consider normal incidence. So light is shining perpendicularly. What is the pressure? The pressure is force per unit area, 1 over area. Yeah, the average momentum per unit time. Force per unit area. Oh, I don't want this vector. It's normal, right? Just shining down. So what we're going to do is we're going to wait for delta t seconds. So in delta t seconds, the wave may have been originally somewhere here. And so this would be the distance c times delta t. Yeah? And let's say this has an area A, this part.
What actually defines I know you're saying that's the area of what?
So you have some sort of a perfect absorber, something that will absorb light.
So it's the area of the perfect absorber.
Area of the perfect absorber. And we're going to wait for delta t seconds. And whatever momentum is in here, this is c times delta t, would have made it to the surface. Okay? So, and what is the momentum density? I forgot the expression for that. It is equal to 1 over A the momentum density. Again, I'm not going to work it as vector, so it's just G. That's the density. It's the average of that times the volume. That's because that's the density. So the volume is area times C delta T over delta T. C is delta T over delta T. So the radiation pressure is just, comes out to be a nice expression. It is just. So notice in my usual notation, momentum is a lowercase p, pressure is that. This is for a perfect absorber. What is the, what if it's a perfect reflector? No, it'd be twice as much. It is initial minus final. Initial is this way, final is opposite direction. It's a perfect reflector. So easy for me to do. Small step for chalk kind. Yeah? None of this is difficult, but we are plowing through so much notation at this point, right? That is simply just the nature of the beast.
Another
Yeah.
question. When we're talking about energy density
Yeah.
and things like that,
Yeah.
we have that E naught term that tells us the amplitude of the wave. When we say that higher frequency things have higher energy,
Yeah.
where does that
Correct. That's a very good question. So, I think, did you take modern physics?
Yes.
So we talked about this problem when we studied photoelectric effect. You would think the energy is square of the amplitude, classically speaking.
Yeah.
And amplitude is E0,
Yeah.
so you have square of the amplitude. But photoelectric effect, the energy depends on the frequency of the photon
Yeah.
and not the amplitude of this.
Yeah.
Oh, that is a classical quantum, classical manifestation of it. This is a large-scale classical electromagnetic field. That's how they behave. But when you go to individual photons,
Yeah.
it is the frequency of the photon. There are so many things embedded in this. See, on the one hand, energy density is U. Momentum density is U. So now that you mentioned, there is classical, there is quantum, there is relativity built into this. I don't know how much modern physics you remember. And what is that formula? M squared c to the fourth is equal to energy squared minus momentum times c squared. Correct? So let's, if this is true, it's true in density too. So if that's the case, let's say in the density version, this would be U squared minus P, which is momentum, U over C times C squared. Last time I checked this math, I get, which is indeed the mass of a, yeah. So, relativity dangles here. Quantum mechanics does not. Yeah, I don't think I can give you a better answer as to why the frequency of a photon is connected to all this. Yeah. So that comes from quantum electrodynamics. And frankly speaking, the quantized electromagnetic field, I don't think I've worked out that problem. I've not even seen that problem being worked out. I'm going to look for it. If not, that's a good thing to either solve or work on. When I say solve or work on, it may not be easy to solve. So if you cannot solve it, you can only work on it. So let me get to the, again, none of this is difficult. We have done the difficult part. But let's, at the end of the day, we're going to talk about reflection and refraction. But we have to get there first. So at least I can get started and talk about waves and matter. So what we want to do is get to electromagnetic waves in glass, for example. A linear dielectric. Yeah? So whenever we talk about this, we have to go back to the drawing board and look at Maxwell's equations. So let me, I'm going to assume that rho free, well, let me write out the equations. Yeah, I think I would assume that rho free is 0 and J free is also 0. There are no bound charges, just a vacuum field propagating, except, sorry, not vacuum field, just an electromagnetic field propagating in a material. Think of, for example, when I say material, now we should be thinking of, say, glass or water. Obviously, it has to be transparent. Yeah. So the equations are easy. This one is always 0. And the equivalent of here, this would be rho free. But we get 0. And then we have Faraday's law, that doesn't get changed. Del cross E dB dt, and then I have del cross H is equal to d dt. But and there's a J free term here, but that's also 0.
Why did our cross E? Why we're not crossing over T in this case?
Oh, look at the expression. Go back to matter. That's the equation.
Yeah.
Yeah. So then we're going to specialize to linear media. We have D equals what? Epsilon naught E, correct? And then H equals 1 over mu, not epsilon naught, sorry, epsilon. That's what makes a dielectric medium this way. And 1 over mu. So let's very easily write out the equations. Well, divergence of B equals 0. Divergence of E equals 0 because epsilon is a constant. We're talking about in the medium. Right? Then we have this guy, del cross E minus dB dt. And this is going to be del cross B. So there's a mu naught over there. There's an epsilon naught over here. Sorry, not mu naught and epsilon naught. There's a mu over here, an epsilon over here, which I'll write it as this looks exactly like the previous case, except now the velocity is what? Epsilon mu instead of epsilon naught mu naught. So this is typically written as see, I got this to be speed of light. And whatever is this, oops, epsilon mu divided by epsilon naught mu naught. Then I get V equals C over N. And you guessed it. What is this N? Index of refraction. That's what we're going to call index of. Okay? Now, what I'm not going to do the actual refraction problem. It'll be done in 2 stages. First, we'll consider the simple case of normal incidence, just so that we don't have to mess with angles, and then we'll talk about oblique incidence. But I want to state 2 expressions that come out to be exactly the same. So the energy density in this case, nothing changes. You know, the Maxwell's equations has just been modified by this, right? So it really becomes 1/2 epsilon E squared plus 1/2 1/2 mu E squared. So the energy density formula, epsilon naught and mu naught gets replaced by epsilon and mu, and everything, it's true of everything else. For example, the Poynting vector becomes 1 over mu, because why would the analysis change? It's just linear media. And momentum density, well, guess what that is? Epsilon yeah? So I think this is a good stopping point. Any questions?